12.4 Impossibilities of Dominant Strategy Implementability. In the previous sections, we saw an interesting contrast between deterministic and randomized truthfulness, where the key difference seems to be the dimensionality of the domain. We now ask whether the source of this difficulty can be rigorously identified and characterized. What exactly do we mean by an impossibility, especially since we know that VCG mechanisms are possible in every domain? Well, we mean that nothing besides VCG is possible. Such a situation should be viewed as an impossibility, since 1. Many times VCG is computationally intractable, as we saw for CAs, and 2. Many times we seek goals different from welfare maximization, as we saw for scheduling domains. The monotonicity characterizations of Chapter 9 almost readily provide few easy impossibility for some special domains. See the exercises at the end of this chapter, and in this section we will study a more fundamental case. To formalize our exact question, it will be convenient to use the abstract social choice setting introduced in Chapter 9. There is a finite set A of alternatives, and each player has a type valuation function V which maps from A to R that assigns a real number to every possible alternative. Vi of A should be interpreted as i's value for alternative A. The valuation function Vi dot belongs to the domain Vi of all possible valuation functions. Our goal is to implement indominant strategies. The social choice function f which maps from the product of v1 times v2 and so on times vn to a, where without the loss of generality assume that f which maps from v to a is onto a. From Chapter 9 we know that VCG implements welfare maximization for any domain and that FI maximizers are also always implementable. Definition 12.23 FI maximizer. F is an FI maximizer if there exists weights K1, K2, K3, and so on until Kn, and the set Cx with x in A such that for all little v in capital V, f of little v is in argument maxima of the set summations of the ki times vi of x, summing starting with index I equals to 1 to index I equals to n plus cx, and where the maxima is taken among all x in A. The fundamental question is what other function forms are implementable. This question has remained mostly unexplored, with few exceptions. In particular, if the domain is unrestricted, the answer is sharp. Theorem 12.24, suppose the size of A is greater than or equals to 3, and Vi is equals to R to the A for all I, then F is dominant strategy implementable if and only if it is an Fi maximizer. We will prove here a slightly easier version of the sufficiency direction. The proof is simplified by adding an extra requirement, but the essential structure is kept. The exercises give guidelines to complete the full proof. Definition 12.25 Neutrality. F is neutral if for all little v in capital V there exists an alternative x such that v of x is greater than v of y for all I and y not equals to x, then f of v is equals to x. Neutrality essentially implies that if a function is indeed an Fi maximizer, then the additive constants Cx are all zero. Theorem 12.26. Suppose the size of A is greater than or equals to 3, and for every I, Vi is equals to R to the A. If F is dominant strategy implementable and neutral, then it must be an Fi maximizer. For the proof, we start with two monotonicity conditions. Recall that Chapter 9 portrayed the strong connection between implementability and certain monotonicity properties. The monotonicity conditions that we consider there are stronger and are not necessary for all domains. However, for an unrestricted domain, their importance will soon become clear. Definition 12.27. Positive association of differences PAD. F satisfies PAD if the following holds for any v prime in capital V. Suppose f of v is equals to x, and for any y not equals to x, and any I, vi prime of x minus vi of x is greater than vi prime of y minus vi of y, then f of v prime is equals to x. Claim 12.28. Any implementable function f on any domain satisfies PAT. Proof: let v to the I equals to v1 prime, v2 prime, and so on until vi prime, vi plus 1, vi plus 2, and so on until vn, i.e. players up to I declare according to v prime. The rest declare according to v. Thus v to the 0 is equals to v to the n is equals to v prime, and f of v to the 0 is equals to x. Suppose f of v to the I minus 1 is equals to x for some 1 less than equals to I less than equals to n. For every alternative y not equals to x, we have vi to the I of y minus vi to the I minus 1 of y is less than vi to the I of x minus vi to the I minus 1 of x. And in addition, v minus I to the I minus 1 is equals to v minus I to the I. Thus, WMON implies that f of v to the I is equals to x. By induction, f of v to the n is equals to x. In an unrestricted domain, weak monotonicity can be generalized as follows. Definition 12.29. Generalized WMON. Weak monotonicity. For every v prime in capital V with f of v equals to x, and f of v prime equals to y, there exists a player I such that vi prime of y minus vi of y is greater than equals to vi prime of x minus vi of x. With a weak monotonicity, we fix a player and fix the declarations of the others. Here, this qualifier is dropped. Another way of looking at this property is the following. If f of v equals to x and v prime of x minus v of x is greater than v prime of y minus v of y, then f of v prime is not equals to y. A word about notation. For alpha beta in R to the n, we use alpha greater than beta to denote that for all I, alpha I is greater than beta I.